Okay, today we're going to go over a few calculus AV theorems. These include the mean value theorem, intermediate value theorem, extreme value theorem, squeeze theorem, and Rolle's theorem. There are a few we won't be going over, such as the fundamental theorems of calculus, but let's begin with the mean value theorem, which states that if there is a function f of x, let's say, and it is continuous and differentiable on a, b, on the interval ab, then there's at least one point where the instantaneous rate of change is equal to the average rate of change. This consequently means that there is a tangent line at a specific point that is parallel to the secant line. And this is because since we're talking about the average rate of change, then you need values that are above and below the average at certain points. And because of this, you have multiple instantaneous rates of change, and one of those is guaranteed to be equal to the average rate of change. Now, as proof on AP test, you must say that based on MVT, there exists a point on AB, and this is what this may look complicated, but this is simply saying that there's an X value on AB, and it's saying that there's at that point the instantaneous rate of change is equal to the average rate of change. Okay, so this is the intermediate value theorem. Now, it states that if there's a function that's continuous on the interval AB, and there's a y value k that is less than f of b and greater than f of a, then there exists at least one x value such that f of whatever that value may be is equal to k. To put this in simpler terms, I'll give you an example. Let's say that there's a graph like this. This is going to be the continuous function here. Let's just say that's x. Let's say this y value is 3, and let's say this y value is 5. Now, if we're given a problem or something asking whether or not there's an x value such that f of x is equal to 4, let's say 4 is k in this situation, well, there will always be an x value that is equal to 4 because the function is continuous over this interval. And that's essentially what IVT is stating. Now, in order on AP test, as proof, you're going to say that since f of a is greater than k, since k is less than f of b, based on IVT, there exists a point such that f of c equals k. Okay, this is the extreme value theorem. Now, it's essentially stating that if f of x is continuous, then there are at least two x values, let's say c and d in this situation, such that f of c is greater than or equal to f of x which is less than or equal to f of d. Essentially stating that the function f of x, if continuous, has a highest y value and a lowest, this should be y value. It has a maximum and a minimum, meaning highest y value and lowest y value. Now you may ask, well, what if the function is simply a flat line? I'll try to make this as flat as possible. Then you can simply pick any point as the highest y value or lowest y value, because over here it states that it doesn't necessarily, one of f of c or f of d doesn't necessarily have to be greater than or equal to, greater than or less than f of x. They could also be equal to. And so that I'm not quite sure if you need to have a proof statement such as this one down here on AP test, but it wouldn't hurt to have. And it's essentially stating that, again, any function has a highest y value and lowest y value, even if those two are equal. Okay, this is the squeeze theorem, and this is quite an interesting one. It states that if there's a function, let's say h of x, if it is less than f of x and greater than, if it's greater than f of x and less than g of x near a certain point, if it fits both of those conditions, and f of x and g of x converge at the same value at that certain point, then h of x also converges at that same value. And that may sound confusing, but hopefully it should make sense. Let's take a look at this graph here. Let's let this blue line represent h of x, this red one represent f of x, and the green one represent g of x. We can tell that when x equals 0, both g of x and f of x converge at 0. And since g of x is squeezed between these two, then it must also converge at that same value when x is equal to 0. And as a proof statement, you must say that since f of x is greater than or equal to g of x, which is greater than or equal to, sorry, since f of x is greater than or equal to h of x, which is greater than or equal to, which is less than or equal to g of x, and since the limit of f of x from x as x approaches a is equal to the limit of g of x as x approaches a equals a certain value, then limit as h approaches x, limit as x approaches a, h of x equals that same value by the squeeze theorem. Okay, so this is our final theorem that we're going to go over today. It's called Rolle's theorem. It's similar to MVT. However, it states that if there's a function f of x and it's continuous and differentiable on a of b, and if f of a is equal to f of b, then there exists a critical point. Otherwise, or also simply an x value that when derived at that value is equal to 0. So let's go over why that is. There are two circumstances in which f of a will equal f of b. One of those is when you simply have a flat line, right? Let's say this right here is a. Let's say this here is b. They're clearly equal, or I tried to make it straight. Hopefully they look equal. But here you'll notice that the slope is simply 0 because it's just staying the same. It's a flat line. The other situation where this is true is if you have a function that essentially changes direction, if you will. It may look something like this, like we have over here. F of a and f of b are equal, you can see. However, the slope is not equal, meaning that there must be a critical point, or an x value, where the slope will change direction. In this situation, we'll just call it c. The slope is equal to 0, and you can see that f of c at that point is equal to 0, and that's what this Rolle's theorem proves. I'm not quite sure what the proof statement is. I just made this up off the top of my head, but I said since f of a is equal to f of b, there exists a point such that f prime of c is equal to 0 by Rolle's theorem.